Yeah, it's chapter 4, the chapter 4 one's due today?
No,
Oh, okay.
it's assigned today. This box means it's today. That little gray box, right? Due here, oh, write-ups due here. Yes. Well, that's what we're doing. So it's chapter 4, 1, 2, and 3. And that's all Reynolds numbers. So we need to get through one Reynolds number today. Okay. All right, so let's talk about flow. This whole chapter is all about flow and pipe. So you really have to start to categorize what we're talking about, because the next exam will have like multiple topics on it. Like buoyancy is completely different than contained pressurized systems, right? Buoyancy is just like a lake or just water sitting there and we're just floating on top or we're sinking, right? So we're kind of moving into a new area. Is this the way? Thanks. At the end of this, we start into the conservation of energy. So that gets kind of complicated. I want to see how they label chapter 5. Yeah, they go into more power in chapter 5. So, all right. The first part of this chapter is just identifying the difference between laminar flow and turbulent flow. So when we talk about velocity of fluid in a pipe, we're typically talking about the average velocity. So these are velocity curves, where the velocity in the center of the pipe is the greatest, and the velocity right next to the pipe is 0, right at the edge. That fluid doesn't move, just sits right on the edge. Okay. So whenever we're talking about velocity, we're talking about the average of this curve. Yeah.
Is that the same reason why like jets their intakes are offset at the inches, because the air sits on the plane?
Yep, that's exactly right. And they're also inverse cone. Yeah, they're not like this. That would add a lot more friction to the air coming in. It would also spin it around. They're like this, so the air coming in is a nice laminar flow. It gets sucked in. Absolutely. And then a turbulent flow is a little flatter, actually. And they should have made this a much lower graph because it's got a lower velocity, right? But a turbulent flow, it's actually closer to average across it than a laminar flow. Laminar flow is this like really smooth flow where not all particles, but most of the particles are moving in the same direction, not interfering with each other. When you take your sink at home and you just barely turn it on, and it's nice and clear if you don't have some kind of weird aerator on it, right? You just barely turn it on. It's just, you can see the water, you can see all the way through the water, and it's just flowing nice and smoothly. Most of the time when you turn that sink fully on, then it's like this spray, right? It's just all messed up. So that's like the easiest difference between a laminar flow and a turbulent flow that we all probably experienced. But the turbulent flow, it can be beneficial. We use this sometimes, like in the mixing that we talked about earlier. If you wanted two fluids to mix, you could put them in the same pipe and make it turbulent, push it fast enough, and out the end, you're going to get a nice mix out of that. So also, we often aerate water. So that would be the way to do it too, is to get it turbulent. All right. The disadvantage of this is we're going to lose energy. And that's kind of where we're moving towards. We have moving water or moving fluid, hydraulic fluid, a lot of different kinds of fluid. They're used for power transmission. So, I mean, the basic example of that is most of us will have hydraulic brake systems on our vehicles. When you hit the brake, you're really just pushing a plunger in a hydraulic system and moving that hydraulic fluid through the system down to another plunger, right, that pushes on your brake. I mean, the basic system. So we use it to transmit power. A lot of pieces of equipment in industrial settings use fluids for power, like air, for example, right? Maybe you have an air compressor at home. Maybe you can plug something into your air compressor and it works, right? Could be a sander, could be a drill. There's lots of tools that can be driven by air. So that's a perfect example of, well, what if I had 400 feet of air hose? And I have 60 PSI at my compressor. And the air hose goes, you know, into 3 rooms, down the stairs and into a bathroom. And that's where I'm working. Am I going to get the 60 PSI at the tool? Probably not. What if I have the hose coming and then I put a T in it and now I have one person driving a tool and another person driving a tool with my 60 PSI? How much can I put in there, kind of thing? How much loss am I having in that hose? So that's kind of where we're heading with the fluid inside of a pipe. Okay. So the first thing we want to know is, what do we have? Do we have turbulent flow? Do we have laminar flow? Which one is it? And the way to get that is with the Reynolds number. Now, it's not super precise. To get a really precise Reynolds number, we'll do it another way also. But to get a really precise Reynolds number, you have to go through much more detail than just the velocity. Okay. But this is a good start. The equation, they give it as N sub R, Reynolds number. The values we're looking for are below 2000. That's going to be described as smooth or laminar. So if we have 2000 or less, we're laminar flow. Okay, we'll run the formula in a second so you can kind of figure out how it works. If you're 10,000 or above, you're turbulent. It's a big range. So from 2,000 to 10,000, we're just not sure. Okay.
Is there a name for like an in between? Is there a mix of the two where it's
There's
somewhat
not
limited?
really an. The only thing I have ever heard is like strongly laminar.
Oh,
And I've never heard anything for turbulent. Other than
Mildly
just turbulent.
turbulent.
Yeah, potential. Yeah. So you can kind of get a feel for that from the range. Like if I ended up with like a 2,500 number, I'd be like, oh, we're pushing towards a laminar flow, right? Might have turbulence if I have too many 90s or something that would build it up. So, you know, if I was come up with a 30,000 number, I'm like, oh, that's definitely turbulent.
So is there like essentially pockets within that range that are like,
Yeah, there is. Yep. Depending on the wall smoothness.
Okay.
So there's more characteristics to go into this other than just viscosity and velocity. So this calculation just deals with velocity. That's the upper V. And I make that as just a V. So my velocity when I write it is just a V. Okay. They do kind of a italics V. And then my viscosity, I make kind of more U-ish. So I think there is also just a Greek letter V of some kind. So just make those two different because they're in the formula together and you don't want to get them mixed up. And then D is the inside diameter. Okay. So you've got to know the viscosity of the fluid that you're pushing. Yeah.
would it be possible to like inflate the viscosity by messing with the surface?
Of the pipe?
Yes.
Not in this formula. This one, they just want that property.
So they're not pushed.
They're not, no. But we'll add factors to it based on the material. So like smooth PVC, it's going to be less possibility for turbulence. Rough, like metal, black pipe, cast iron pipe can create, it has, even in a laminar flow, cast iron pipe has turbulence on the edge. So those edge particles are kind of swirling. And then the middle is still laminar. So the surface matters. This formula does not take into that consideration at all. So it's a real general, like, hey, I wonder if we're anywhere near turbulent, you know, and you calculate it and you get 1,500, you're like, oh, no, we're good. We could probably run any kind of pipe, probably. All right. So for example, let's say we have a garden hose. Everyone has one of those or has been around one of those? How long are they? Yeah, they can be like all these different sizes. I think the shortest one I ever see is like 25 feet.
Yep.
And then they definitely have like 150 feet. In this equation, is length of pipe in the equation? No. So again, you have to kind of sift through the information. If you're trying to determine laminar and turbulent, you don't need length. We don't need that. What do we need? Diameter. So how big's a garden hose? Any idea what the inside diameter is? ID, I think 3/4 is pretty close. And they want the ID, the inside diameter. So often, like if you order up 400 feet of 1/2 inch PVC, is that the inside diameter, 1/2 inch? No, not necessarily. You need to look up the specifications of whatever you're working with and make sure you have an inside diameter. So that's the number we want. So we'll say it's 3/4. What's that in decimal? We have sound on. Sound never works. Testing 1, 2, 3.
There it is.
Now it's good. Whatever. Let's continue. So what else do we need? Right? It's diameter, it's velocity, and it's viscosity for Reynolds number. We need velocity. Garden hose, full blast. What do you think? It's hard to tell velocity, but what about like garden hose, full blast in a 5-gallon bucket? What do we think there?
How long will it take to fill?
Yeah, like how long would it take to fill a 5-gallon bucket?
30 seconds.
No, at least a minute, 2 minutes, maybe,
I'd say 2 minutes, sounds good.
minute and a half, I think.
About 3 to 4 minutes, 3.5 minutes.
Yeah, it's in there somewhere, right? It's definitely like on the low side. It depends on your pressure, right, of your home. So some of us are on a well, some of us are on city water, some of us are on city water at the end of the housing development. Some of us are on city water at the beginning of the housing development. It can vary anywhere from 60 PSI down to 40 PSI. Right? So who knows? So we'll just make something up. We'll say it takes us 4 minutes. 4 minutes to fill 5 gallons. So this is the other concept that I want you to try to get your head around, is what's called flow rate. Flow rate deals with a volume per unit time. So if we say, oh, we can fill 5 gallons in 4 minutes. I can write it that way, and that gives me a gallon per minute. Right? That gives me a flow. Flow is called Q. And Q is super handy. If we know the flow rate, like, and you can get it by experimentation sometimes, right? For example, at home, you could take a garden hose on a 5-gallon bucket, time it, and you could get 5 gallons per 4 minutes. So what's this number just per minute? Thank you. 1.25 gallons per minute. All right. So Q is super important because Q also equals A times V. What's A? Area, almost always. And V is velocity. I should make this a small v because they use a small v. So that is area times velocity. So if you know Q and you know your cross-sectional area of your pipe, you can get the velocity. I mean, what's your guess? Garden hose, you watch the particle come flying out of there. How many feet per second does it come out of there? It's gonna, if it's gonna go this far out of your garden hose, that's just shooting from here to the end of the table, right?
I guess a feet per second.
Yeah, it's less than a second. It might get 1001, it might get to the end of the table in
Okay.
a second, right?
Yeah.
That would be like 10 seconds to get that distance, or 1 second to get 10 feet.
Right.
Okay, so but it's hard to, like, when you look at something, it's hard to, like, what's the velocity of that? Oh, it's hard to tell. I don't know, but we can calculate it. So if we know that we have 1.25 gallons per minute, we kind of need to get rid of the gallon thing because we don't really talk about velocities with gallons. We're going to want cubic feet per second or cubic feet per minute. Okay, so a conversion that we use a lot is how many cubic feet are in a gallon. Anybody know? Somebody Google it for me. How many cubic feet in a gallon?
7.48. Divide the volume value by 7.48.
It's not that many cubic feet in a gallon. It's going to be less than 1.
Oh, that's the formula for going from gallon to cubic foot. So 0.11 or 1.
So are you saying there's 7.48 cubic feet per gallon?
Yes, that's got me. That would be backwards.
Or 7.48 gallons per cubic foot?
A gallon divided by 7.48 will give you.
We need a conversion. I bet it's, yeah. 0.134. Is that right? Did I write that correctly?
Yeah.
All right. Gallons are small. Oh, they're really pretty small. Okay. So notice the way I wrote it. Why did I write it that way?
You cross gallon on both sides.
Yeah, so I can do my unit analysis. I can get rid of the gallons, right? So now I have feet cubed per minute. And that's Q. I'm gonna set it equal to A times V. What's our area? There's our diameter, right? 0.75 inches. We might want to put that in feet. Because I want all the feet the same down here. I want feet cubed. And I kind of want feet per second for my velocity. That's a common velocity. So what is that? 0.75 divided by 12?
Yeah.
Yep. 0.0625? 0.0625, that's the diameter squared. Pi d squared over 4 is the area. If I want to use the diameter. That's the diameter area formula. Pi d squared over 4. And velocity, v. So area, velocity, v, q, q. This has given me the velocity out of the garden hose. Right?
Where'd you get the 0.625, 0.0625?
We took the 0.75 and divided by 12. Because we wanted feet. I should have put a unit in there.
Oh, got it.
Yeah, we took the 0.75 divided by 12.
No, because I already had the area and I was confusing my area with.
Oh no, this is my area formula right here.
Yes, I already did that.
Area formula. All right, what do we get for velocity? Give me a number. Engineering firm is very quiet.
Are you looking for the area number?
No, I want the velocity. You all are capable of solving this equation.
About 3.4,
How much?
3.412.
There's our first number. Feet per second, right? We need confirmation though. Don't forget to square this.
I get the 0.1227.
That's different.
I think I multiplied by 4 instead of 5.
I got 54 for 597.
Oh, so we're getting some different numbers. What was yours, Jorge?
0.1227.
Feet per second. And Juan,
54.597.
54.597 feet per second.
Okay, I would like to offend my.
Everybody gets a vote here. Uh-oh, there's 2 here,
I confirm that as well.
3 there. How many of you are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We need 13 votes. You can just fake it and just guess at one.
Yeah, 54 cents.
Like, yeah, you're with one.
I'm thinking, yeah.
Same with the bottom one.
Anybody else actually calculate?
I did. I did. I got my vote.
You 54? I
No, I haven't voted yet, but I have a vote.
think you should vote.
I got the bottom one.
So these actually have one vote. So we're at 8. A few more folks need to vote.
Yeah, I was like, so.
It's getting more popular. I think that's just because you guys are looking at it going, it must be the bottom one. Gotta calculate it.
I feel like that's really big.
Gotta calculate it.
Like,
It is
yeah,
big.
spat out.
It's big.
Yeah.
But we guessed at the flow rate, so our
Yeah.
flow rate might be pretty high. 5-gallon bucket, garden hose, takes a while. You're standing there a while. All right, I get the bottom one. There it is, 54 feet per second. It's traveling fast. Like, if that's true, if this is all true, it's traveling very fast, right? Common well outputs are like 13 gallons per minute. That's a pretty common output of a well. Low would be like 5. I think mine is like 18 gallons per minute it'll put out. So they're realistic flow rates. All right, so now we have a velocity. We can go after our Reynolds number. So step 1, unless they give you the velocity, is you got to find the velocity. On the homeworks, I don't think you have to find the velocities. I think you're just going to calculate the Reynolds number. Okay. So to get the Reynolds number, we take the diameter. And if your velocity is in feet per second, you want your diameter in feet. You want these units to work together. So be careful with that. We already know it's 0.0625 feet for the diameter. And now we know our velocity is 54.597. And then we need the viscosity of the fluid. What kind of fluid do we have? Water. You remember what the viscosity is?
1 times 10 to the negative 5.
And the units are feet squared per second. What's the unit of our velocity? Feet per minute. Right? Isn't that what we got? Oh, we get, oh, we got feet per second. Wait, it should have been minute. That's why you all are thinking that's too fast. I was gonna say, I think we did minutes. So now it doesn't feel so fast, right? 54?
Yeah,
Because we get a full minute.
that seems nice.
Yeah, that's a much more realistic number. Why is it per minute right here? All right, so we are per minute up here. But our viscosity comes to us in per second. And we want this to be a unitless number. It's got to be unitless. The Reynolds number is unitless. So what do we have to do?
Y versus X.
Yeah, we got to put a factor of 60 in there somewhere. And we got to put it in the right spot.
Right, then a minute section.
So yeah, if we do it up on top, right, we can say 60 seconds per minute. So we got to reverse that. So we have to write like 1 minute per 60 seconds. So that and that cross. So that puts the seconds down below, down here. But this is in the denominator of the denominator. So it flips up and then crosses. So the seconds do cross. Feet squared, feet squared. Units are a big problem with Reynolds number. Like that's where you can make the mistake. Reynolds number itself, that's a pretty simple formula. But it's the units you put into it to get it unitless.
Could you not multiply 60 by the denominator?
You could, yep, absolutely. You could convert the bottom one. Yep, so just be careful with how you do it. What do we get for our Reynolds number now? Another voting time. Another class participation.
So we're multiplying the numerator by 60?
60, when we do this, right, 1 over 60, 60 is really down here. Yep. But definitely write those units out so you understand that they cross cancel. That's critical.
The ranges for the flow again.
Less than 2,000 laminar. Over 10,000 turbulent.
Over 10,000.
Over 10,000. And that's within the pipe. Often you get turbulence outside the pipe. Like the water that we see coming out of the garden hose is like white, right? It's clearly aerated and all kinds of turbulence. But that's exit. This is the velocity inside the hose as it's moving through the hose. So like, 10 feet into the 50-foot hose kind of thing. What do we get for a Reynolds number? What's my numbers?
5,687.19.
5687.19. Anyone else got a number?
Yes, I got that.
Uh-oh. Anyone have a different
Wait,
number?
no, 5.687, yeah.
56871875. So what do you think? Laminar or turbulent?
Oh, no.
Turbulent.
Don't know. We don't know for sure. It's definitely not under 2,000, right? It's not over 10,000. So it's not purely turbulent, but it's also definitely not purely laminar.
Anything under 2,000 is definitely laminar.
Yep. Less than 2,000.
So how would you describe the in between?
As just like I did, definitely not laminar, but not fully turbulent. So that just means like when we do energy analysis, we're not going to get a completely good approximation of what's going to happen because it's not laminar. Laminar is fully forecastable what's going to happen. Turbulent is just less forecasting going on. And most of the time we don't want turbulent flow, like in the applications that we're going to talk about. They're going to be laminar flows. But we need to, check it and verify it.
Something that you would maybe do would be like find what like diameter of pipe or like flow. would
Yeah,
get that
exactly.
vertical load
Yep,
down.
that's exactly right. That would be next is, okay, what if we need this to be laminar flow? What kind of velocities are we looking at? So you could either lower the velocity, change the diameter, right? Because we got the velocity using area, right? So those are the variables you can change. So, and each situation is different. Sometimes you need the velocity, right? And you don't care as much about laminar or turbulent flow, as long as you're getting the velocity that you need out the end. And other times you care about the opposite, like we don't care about the velocity, we just need this thing to be laminar, so it doesn't chew up equipment. So turbulent flow will chew up metal, it'll eat metal. So, and it causes all kinds of problems within a fluid system. So I'm a wing foiler, right? And a foil goes through the water and it needs to go through very laminar. If it goes through turbulent, in other words, if it cavitates, so if you've been in a boat before that cavitates, you can lose steering. That means your rudder builds an air pocket around it. So when you get turbulence, you can actually create air because it's like turning water into air. And if you get an air pocket around a rudder that's supposed to be steering in a laminar flow, then you no longer have steerage, right? Same with the foils, it goes through the water, if it crests the top surface, that'll pull air around it, and then it's just useless, it doesn't do anything. Big crash
What's the
comment.
formula again? Think
Huh?
I did it wrong.
Hmm?
Think I did it wrong, can I see the formula for the Reynolds?
Right here,
Uh,
yeah, you can't
oh,
forget this,
you're right.
don't forget the 60 down there. Yeah, I got that number.
That is wrong.
So turbulence causes a lot of problems. Surfers get turbulence all the time. Like if you overspeed a fin that's on your board, it will cavitate, get an air pocket, and now the surfboard has no steering and they're down. So it's pretty,
A
Calm.
wave. Wave is laminar and then goes turbulent.
yeah,
right?
absolutely. Yep.
Can
Exactly.
laminar flow still about something?
Yeah, oh yeah, it can still erode something. Yeah. Like,
Like it is still like eat through metal, like turbulent flow?
yeah,
Just
it
takes
would
longer.
not, a laminar flow is. I don't know that it can affect like hard materials, you know, like a metal.
Yeah.
But like obviously creeks, a lot of those are laminar flow and they can just eat away the earth kind of thing, so. All right, that's it. You have 3 homeworks, Reynolds number. See you Wednesday.
Water jet. I got a water jet cutter.
Yeah.
Let's start it.
Yes.